All right, so let us revisit what our classifiers were in both versions of the problem, that is the primal version and the dual version, right? So I have the primal version in which my classifier, meaning my g of x, looked something like this. It was the sine of w, and if this is the optimal, w transpose x plus b star, right? And then in the dual version, we can get these w's and b stars, right? And then plug them into the final hypotheses and get the same result. So again, what we are trying to do now by like re-looking at the dual is that we're trying to address the issue of trying to get rid of dependence on dimensions, right? For example, the dependence on the actual feature vectors. So we know when we transform these like x's, the xn's and the xm's to some z space, that results in some more complex features. And so that's why we are trying to address this problem now. You can tell that this can create really, really complex versions of the problem for us, right? So let's look at the dual version, as I said. So also look at the dual version first. What was g of x? Well, g of x is again sine of w star x plus b star, but there's like another way of like getting to that. And so what we are doing is in this dual version is we get g of x equals, and that is also sine of w star, but w star has been calculated using alphas, right? So sine, and then n is from 1 up to n, alpha n star yn xn transpose x, right? So this part here was nothing but the w star, right? So that's that. Of course, plus b star should also be there. So there's no space left. I'll just like write plus b star here and just say like where my b star is y of s minus, again, substituting for the w's, n alpha n star yn xn transpose xs, because we know why xs comes in here. We talked about that earlier. All right, so because we have like some form of like representing my w's, and when we just like rearrange terms, we have this term here and this term here, right? And overall, we have like the dependence of this final version of my dual problem on my alpha n star, my yn, my xn, and also on x, right? And if we think about the dependence on this term, that's why I underlined it, just like xns and xn, we can tell that, of course, that dependence is there, but it's there in an arbitrary way. It's not direct. And what does that mean? Well, the computation of my b star, this thing here, and hence the dependence on xn transpose xs, well, it depends on the dot product of xn and xs, like in general. So this is nothing but a dot product. And same is the situation here as well. It's just a dot product of these two. But well, like this doesn't like really ring a bell, because okay, so what if that's a like a dot product? How does that help? Because if I'm looking at this equation, it like really seems that yes, this is a dot product, but I'm going to need the entire data, just like the k nearest neighbor, right, to in order to achieve this. So what exactly should I like? How does this like dot product help me? If you remember in the example before, and although that wasn't like a representative example, I would say in the sense that we did get like one of the alpha n's equals 0, right? In this example here, right? This alpha was 0 because this wasn't a support vector and the other were non-zero. Well, why is that discussion coming up now? That's because like in most problems, in most situations, right? Most of these alphas are 0, because remember, let me write down, most of alphas are 0, because like the alpha s greater than 0 are the ones that are exactly the alpha s, which is like my support vectors, right? So in terms of my computation, I only need these in my final hypotheses, right? So this in turn, like these alpha s are the only usually ones that we need. This is pointing to like huge saving in computation, right? Why? Because like I know that most of these are like zeros. Like in terms of like what I mean by need is like we don't have many alpha values that are greater than 0. Okay, So that's the thing that we need in a final hypothesis, and that's a huge saving. Now for the final problem, it tells us, this observation in a certain way tells us that maybe we don't need all the data, right? So maybe we don't need all the data because, like, just stepping back, if you just step back and see, when we solve the dual problem, right? So we have the target values y, and then the optimization variable was alpha, so the target and optimization was alpha. And then we had these data points like the xn's and the xm's, right? And if you remember, we don't need that entire data itself. We don't need to send this entire data to that, like the solution of the problem. We just needed that matrix. What exactly am I talking about? Well, we needed this like G and M, and this is not the entire matrix, but essentially this is like xn dotted into xm, right? So this is xn dotted into xm, right? So we needed the dot product in order to get my like alpha stars or my alpha n stars, right? So in like general, all we needed to solve this problem, right, were these dot products, right? We needed this like g and mth term, which is like the dot product of like xn and xm. So like in general, in the dual definition, we have this like g n m, which is like by my n by n matrix of dot products, right? So matrix of dot products. All right, that's great. And then I have a target vector of like target values. So target vector, which is like my n by 1 vector, right? And then these both lead us to compute. With these, I can compute my alpha n star. And this is what I need for my dual, because then there is just like a one-step computation for my weights and my bias, right? So this entire process of solving this problem essentially depends on my ability to compute dot products, right? So my ability to compute dot products is something that is important to me. And such algorithms in general, and this one in specific, are known as the inner product algorithm. And so this is like a larger family of algorithms that have, like, whenever such properties exist in your algorithm, then that's like an inner product algorithm. So what exactly is this algorithm doing? Well, this is telling us we don't even need my data that I have. I just need the dot products to run this like optimal hyperplane, right? This is what this is telling me. This information is telling me. Well, so let's see how that is possible. So number one step in this inner product algorithm is that suppose you give me a function. So suppose you're giving me a function k that acts on like two vectors x and x prime, and it gives me the dot product of x and x prime. I mean, I understand that, of course, this function must be doing something. But from the perspective of the algorithm saying, just give me this function and such that it takes in two vectors, right? And then it gives me the dot product of those two vectors. And let me call this function a kernel. Okay, so this is like step one. So what will happen when I have this kernel? What happens to my optimization problem when I have this kernel? Well, my optimization problem would look something like this. So what I'll be doing is like minimize over alpha, right? And nm alpha n alpha m yn ym, and then the dot product would be given by my kernel, which is xn xm, because this somehow would magically just like give me the outcome of the dot product. I wouldn't even like go inside and do anything about it, right? So minimize this entire function subject to my constraints, which I'm already familiar with. So alpha n yn equals 0, alpha n greater than or equal to 0. Okay, so what I do with like this problem, once I solve this problem, I'm going to get my alpha n star, right? So this is going to give me my alpha n star, and then I'm going to get the final hypotheses using this alpha n star. And so just like to write it again in terms of my g of x and the sine function, what exactly I'll have here? The sine of that, right? So the sine of n is from 1 up to n, alpha n star k x n1 x, let's say that's the point that I have, plus b star, where my b star as usual is ys minus n is from 1 up to n, alpha n y n k x n support vector xs, right? And xs is a support vector, of course, and then alpha s is greater than 0. All right, so here I have the solution to my problem. So what exactly is the saving here? Like what exactly I didn't do that I was doing earlier? Well, with just the ability to compute my dot product through this kernel, right, I'm able to get the final optimal hyperplane. So that in with respect to the actual process of calculating every dot product is like a huge computational saving, because the dot product, if you think about it, is just like the dot product. And why is, of course, we're not like going inside and calculating that. Of course, we have a function. Well, that how is that function helping us? That's the question, right? How is this function helping us? Well, this function is helping us because like my dot product, right, is a dot product no matter what the space is, right? So regardless of the space, and this will become clear when we look at a few examples. So this entire process of like getting a kernel to compute the optimal hyperplane, solving for the optimal hyperplane or the optimal hyperplane algorithm is an inner product algorithm here, right? So this is the optimal hyperplane algorithm because we got the optimal hyperplane, but this is like the category of inner product algorithm because it only needs our ability to compute dot products, right? And as I said, the relevance of this algorithm will be made clear when we think about feature transforms and like transformed space. So let's try to talk about them, right? So let's say we have this data, which is like x1, x2, and so on to xn. We apply some feature transform, go to z space. We have z1, z2, and so on to zn. My feature vector doesn't change, right? So y1, y2, yn, y1, y2, yn. Okay, sorry, not my feature vector, this is my target vector. My feature vector, of course, changes because I've applied this transform. Okay, so when I'm in this like transformed space, I need the dot product in that space, right? So basically what I need in my transformed space is like Zn transpose Zm, correct? Or like what happens typically, whatever with like our knowledge of transformed spaces stand, like where it stands right now, we will go into that space, right? And then it's somehow like if we have a test point z, first we'll have that space created, right? And for any test point, let's say z, I will just like go ahead and calculate z and transpose z, right? And then compute the Euclidean dot product, which is like this thing, like usually I'm saying, right? And then come back and like report, okay, this is the classification of my test point. This is the overall process. Now, my question here is like, is it possible to compute this dot product, given that this dot product is such an integral part of our optimal hyperplane algorithm, right? So is it possible to compute this dot product and run the entire algorithm without actually going into Z space? Can we do that? That's the question mark. Like we don't really go with all the data in Z space, but can we do something without going there? So if we can replace the entire algorithms with like variables of Z space, then what happens? Like what exactly are we doing if we have these kernels that are calculating my dot product of xn, xm, right? And so my kernel for xn, xm will correspond to the dot product of zn transpose zm. Similar to that, I'll have like my kernel for xn and the test point will be able to compute this dot product as well. And my kernel for xn xs will be able to compute my dot product for z and zs. Okay, what does this mean? Basically, what I'm trying to say here in this particular like such a like formation is that you give me a function that can produce the same dot product as the one in my z space. right? So this wouldn't be like very straightforward. I would say this like transition from this space to this. But can we like come up with a function that can really do that without like such that I have this kernel that's applied to my original data, and I'm getting the dot product in my Z space, right? Can I do that? And that's an important question, because if I can do that, then I can run my entire algorithm in my original space without even going into the Z space and still getting all the positive flexibility of my Z space. So what do we need to do? What we need to do is we need to construct this kind of a kernel. We need to come up with such a function, because this seems pretty useful. In like with respect to my optimal hyperplane, the dot product is the only thing that I need. And when I'm working in my Z space, again, I will need the dot product. How about I come up with a function that computes that dot product for me in my original space, right? So we'll construct a kernel that can compute dot products in like my nonlinear feature transform spaces without actually going there. And how do we do that? Well, take as inputs the actual data, compute dot products through that function for that space, but never actually go there. So that's exactly what we like really want. And so, of course, this is just like talking and talking, but we really need to look at an example. So let's look at an example. We're going to look at two examples. One is essentially going to take us to the infinite dimension. The first one, I'm looking at the second order polynomial. So this is like example one. Okay, so the first is, as I said, the second order polynomial transform. All right, so let's look at this, right? Let's say I have my x, which is x1, x2, and in my z space, this becomes, from our like prior knowledge, x1, x2, x1 squared, x1, x2, x2 squared. Right? We know that from our prior knowledge. And also I'm adding a square root of 2 here. Like, do not get intimidated by that. It's just like a standard polynomial transform. And for mathematical convenience, we add that, right? It's just a constant. You can have it or you can remove it. Now, if we want to run the optimal hyperplane algorithm in Z space, then we should be computing my Z dot product, some Z prime. And of course, then like that means that whatever transformation I've applied, that on X dot on X prime dot, not dot, but I mean like the phi X transpose dot phi X prime. That's what we need. All right, so let's look at what this is going to look like. And I'm assuming that my Z prime is again like similar to what we got here. So essentially like x1 prime, x2 prime, and then x1 prime squared, right? And then square root 2, x1 prime, x2 prime, and then x2 prime squared, right? So this is this. And so when we are computing like my z dot z prime, what we get is like x1 prime plus x2 prime plus x1 squared, x1 prime squared plus x2 squared, x2 prime squared plus 2 times x1, x2, x1 prime, x2 prime. Okay, a lot of algebra there. And I'm going to like quickly skip the algebra, and so we can like rearrange terms. And of course, this comes from like high school level algebra, where you can like get a form of something like this, which is x1 prime plus x2 prime plus half whole squared minus 1/4. Right? So if you expand that, you essentially get that, right? And what exactly are like these terms here? So these are like the components of my x1 and x2, right? And so my dot product in my z space, which is like z dot z prime, is equal to this, which is nothing but x dot x prime plus half whole squared minus 1/4. All right, so this here is my x space, isn't it? Like this entire calculation is in my x space, and like I'm getting my z dot z prime equal to something that is there in my x space, right? And if you think about it, this is exactly the kx prime that I was talking about, right? So this is nothing but my kx x prime, although this seemed like pretty convoluted here, like how am I going to get that? But here we just like got it, right? So if you think about it, like why is it such an like achievement as such? That's because we don't really physically need to go into the z space in general. Like for any qth, like let's say order polynomial, we can get a similar function or a similar kernel. So that's the power of that result, and you can like go and verify that, and I'm like writing it here. So for any x prime, right, and as I said, a qth order polynomial transform, we have x dot x prime plus half to the power q minus some constant c, not necessarily 1/4, because of course it depends on the number of terms that are going to come up. The important point though here is that this is my kernel, right? So this kernel is equivalent, I would say, to getting the dot product in the z space, right? So this is like get dot product in z space without actually going there, right? So without actually going there. And this is a very, I would say, a huge computational saving, because like now this dot product calculation only depends on the dimensionality of my original x space and not my z space, which would have like created higher dimensional data maybe, right? So that was my example one, to kind of demonstrate that we can come up with a function that does some computation for my input space, such that I don't even need to go into this higher dimensional space and still get the results that I need, because this is my inner product algorithm and I figured that I only need these dot products, right? So in conclusion, after this example, before we look at the second example, what we are trying to say here is that number one, we can run this entire algorithm by simply using the kernel, right? So all we need is the kernel that computes dot products. So that's like my first, I would say, achievement, or like I would say conclusion of this entire process. Second is we are getting huge computational savings, because obviously like everything we did sort of pointed us to the fact that all we need is this function. We don't really need the z space like physically. So I don't need to like take all my data, put it there, and then like deal with the like higher dimensionality issues and all of that, right? A side note here before we look at the second example is that all the analysis we did was for separable data, right? And so this must be coming to your mind, like what happens to inseparable data, or like inseparable when inseparability comes in. So similar to what we did in like the hyperplane formulation, when we said that we can use the soft margin hyperplane where we are allowing some sort of penetration. So the exact same procedure will apply here, like except that in the minimization or my optimization problem will have the origin, like the extra term with the regularization parameter, right? So we'll have that, and some like penetration that was allowed. We saw that earlier, right? So the exact same analysis applies, and in fact, again, we can have a primal dual equivalence, and then we can look at this like eventually it comes down to this like calculation of the dot product, which is like again a part of the inner product algorithms. All right, so that was a side note on inseparable data, I would say. And the second example that we are looking at is essentially to demonstrate what happens when we want to work in an infinite dimensional space. So this is, let me write it down, infinite dimensional space. All right, so what exactly is that? Well, this is like one example, right? So the one example is this is my x. So remember, I'm like going into infinite dimensions, and let's say my x and x prime are something like this. So it's e minus x squared. This is like a very standard way of like expressing this kind of a dimensional data. And so I'll have like x1, 0, x1, let's not have x1, like x to the, so this is just like the powers, not really the ones and the twos, because I'm just like assuming that I have done like the transformation to that higher dimensional space. So x1, x0, x1 x squared, x to the 1, right? And then x cube, x fourth, and maybe so on up to x k, and then it goes on. Like I don't know where it stops, right? So this is my z essentially, right? So I'm just like transforming, and this is like my phi of z. And I also have, like, for mathematical convenience, this term added, square root of 2 over 0 factorial, square root of 2 to the 1 over 1 factorial. So you got the idea, like what's happening here. So for instance, here it's going to be 2 cube over 3 factorial, and so here essentially it's going to be 2 to the k factorial, and so on, right? And this term is essentially added to normalize things here, right? And so all we're doing here is, like, we're considering this infinite dimension transform, and we have introduced some constants along with the variables to keep algebra manageable. And this is my z, right? And so of course I need my z prime that comes from my x prime, and so let me write it down here. So that is like e minus x prime squared. Everything stays the same except that we have those primes. And so square root 2 over 0 factorial, x to the 0, and then x to the 1, square root 2, 1 factorial, and so on, x prime k, sorry, so this has to be prime and prime, k square root 2, k factorial. That's it, right? All right. So now, obviously, if we have to think about the kernel. So if we were to actually go into the space and compute the dot product, then what happens? Well, I'll have like z dot z prime, which is going to be my e minus x squared, e minus x prime squared, and then I'll have these terms multiplied, right? So I'll have like 2 to the 0, 0 factorial, x, and then x prime to the 0, right? And then 2 to the 1, 1 factorial, x 1, x prime 1, and then still x and x prime, right? Not 1. This is just like x and x prime, and then this thing like whole 1. And then similarly, like the second one is going to be x and x prime whole squared, and so on, right? So this like just goes on and on because this is like infinite. And this is a known series. I'm sure you must have come across this. So if we like look at this series, this is like of course pointing to like it must be converging somewhere, and so we have a term that represents this series, and that's like the e to the, because like 2 can come inside, right? This is 2 to the 0, 2 to the 1, and then we'll have like 2 squared and so on. So 2 can come inside, right? And that's the whole point of getting the square roots, because earlier there were square roots, but now they're like some concrete term. And so this entire term is like e to x prime. Okay, so that made our life really easy because now we can simplify these e terms and then bring all of them together. So you can tell just by looking at it. This is like x, this is like a minus b whole squared, right? That's the formula for this one. So I can just like have a minus outside and x minus x prime whole squared, right? So now if you look at it, right, I have come down to a very simple function in like one-dimensional space instead of going into that z dimensions that we're going into like infinite dimensions. And so what exactly is my k here in this case? Well, my k is, my kxx prime in this particular example is e minus x prime whole squared. And what exactly is this kernel like doing? It's allowing us to compute my dot product in my infinite dimension by just being in my one-dimensional space, but just like being and utilizing my one-dimensional space, right? So, and also like this kernel specifically is known as the Gaussian kernel. Okay, so this is the Gaussian kernel. Most generic form of this kernel is essentially E minus gamma, which is like some normalization parameter, or x minus x prime squared. So this is like a more generic form of this Gaussian kernel. But regardless of like the exact form, what exactly have we accomplished by getting this? Right? We have accomplished the fact that although we are trying to compute the dot products for the higher dimensional space, we can still do that in my one-dimensional space, right? So this is a huge computational saving, and this is a huge result for us, because now We can work in the infinite dimensional space without actually going there, but just by getting the right kernel. All right, so this kernel actually seems important in this entire process, right? Kernel is extremely important. And if we look at our sequence, right, what we have done until now is actually a wrong sequence. We can even do better than this. What, like, usually we select a kernel and it corresponds to some Z space, right? And we don't need to know that space because, like, we can run the entire algorithm without actually going there. So, for example, we can do infinite dimension polynomial regression, right? And we don't need to go there. So as long as we are able to select the right kernel, we are really good. We don't really need to do anything else. And there is this theorem called Mercer's theorem that says that you can think of any kernel, as long as there are certain restrictions, not, I wouldn't say restrictions, but certain requirements. So for example, it should be symmetric, positive, semi-definite, or positive definite, right? So symmetric, positive, definite, as long as it has these properties, right, it will always correspond to some feature space. So regardless of that, as long as, like, I can pick up an appropriate kernel, I can work in that higher dimensional space, whatever it corresponds to. So we don't have to do it the other way even. So there's like one step saving in that. Like, you don't have to essentially follow that sequence of like getting the z dot z prime. Instead, just like pick a kernel, as long as it has like certain properties with it, it is going to be like pointing to some space, right? Some feature space. And if it's like a higher dimensional space, I'm already there, right? So this is an extremely, extremely powerful result because, like, we can do transformation to infinite dimensions. That's like the highest level. Most likely we don't even need to go there. But we can do that transformation to infinite dimensional space without actually going there. So that's an extremely, extremely, so we can work in like infinite dimensions. That's the highest level that we can go to, is essentially what I'm trying to say. All right, so let's like essentially try to summarize what we did when we did this kernel trick. First of all, the first point that we noticed here, that it is like computationally feasible to learn in infinite dimensional space, right? So infinite dimensions are computationally feasible, and that is because of my K, my kernel, right, which is nothing but a dot product in feature space in some higher dimension, right? Now, this is also like going back to our foundations, pointing us to something very important. Well, as we start going into this infinite dimensional, if not exactly in infinite dimensional space, but somewhat close to infinite dimensions, right? My hypotheses will become non-falsifiable. And this should ring a bell. Basically, I will always be able to separate the data because I'm like in such higher dimensions, right? And so the moment we have non-falsifiability in my hypotheses, we know that we are losing the link in between E in and E out. We are losing that link, right? And so that's also not good. We cannot just like keep going and going in infinite dimensions, because then like every data set, everything that you have is essentially separable. Doesn't really give us an idea of like doesn't really give us the answer to the problem that we are trying to solve, right? Okay, so whenever we are losing the link between E in and E out because of like higher dimensions, then what do we need to do? Well, second point here is that we need to regularize, believe it or not, and regularize a lot, I would say, in this situation whenever we are working with higher dimensional space. So basically what we are saying is we have to do a maximally regularized hyperplane. So the max margin with maximally regularized um, hypotheses, right? So we have to regularize and maximize that in order to get my final hyperplane. So effectively what we are saying is we will still use fewer degrees of freedom because we will constrain our model, because the moment we constrain our model, we will bring in the relevance of the relationship between E in versus E out, right? And that is possible only through regularization. So we will maximally regularize to get the optimal like hyperplane. That is extremely important. All right. So basically what we're doing here by regularizing is that saying that we will survive when the number of support vectors is small. Although like we are saying that we should start with like a huge number in infinite dimension, of course, but then we will bring in regularization and control that. So no matter like how many degrees of freedom we have, like by going into the infinite dimension, essentially we will still be working with a smaller number of support vectors, right? So smaller number of effective, smaller number of support vectors. So that's the fourth observation. And just like two things that should come together for an optimal hyperplane. So after like talking through this part, there are two important things that should come together in order to get the optimal hyperplane. First of all, the computational feasibility, which we of course achieved using the kernel. And the second part is that we cannot like ignore the learning process. So for the learning to work, we need regularization. So both these need to come together in order to get the optimal hyperplane. So this is an important aspect of like the kernel trick, that of course we have the ability to work in higher dimensions, but then there is this issue of losing control of E out, and so that's why regularization is an important component of this entire process. All right, so with this I end this lecture and this video, and see you in the next lecture, which most probably is the last one.